Up until now, we've been focusing primarily on electrostatics. This is the branch of electricity in which charges are stationary or non-moving. For instance, given this configuration of stationary charges, find the electric field or electric potential at a certain point. Given this collection of capacitors, find the charge on capacitor C1, specifically once charge has stopped flowing. For the most part, charge is non-moving in the problem sets we've had until now. In situations in which charge might move, we say we just wait for a little while until charge has stopped moving, and then take whatever measurements we need to make. But now we're ready to move on to something much bolder, electrodynamics.
How about this one? I call it bold and brash. More like belongs in the trash!
Sorry, I must have missed that one.
Electrodynamics concerns itself with moving charge. In other words, how might we make measurements involving moving charges? This is super exciting. We've had some motion-based animations before, but now we get to see a lot more just by virtue of dealing with moving charge instead of static charge. So let's get moving. Any introduction to electrodynamics must involve a discussion of electric current. Not all electronic devices contain capacitors, but literally every device that involves electronics that you can think of, from computers to cell phones to airplanes to air conditioners, toaster ovens, they all involve electric current somehow. By definition, electric current is the flow of charge, and electronic devices can't operate without involving a flow of charge somehow. So we must discuss how to quantify the idea of the electric current. We usually think of electric current as flowing through conducting wires, like maybe this wire here. So why don't we start our journey by peeping inside one of these wires? We can model a wire as a cylinder, and just for the sake of simplicity, say that this cylinder is perfectly straight and has a constant cross-sectional area A. Now imagine if we have positive charge moving inside our cylinder toward the right. This means we would have electric current. We run into just one little issue though. Is this how current actually works? Current, we know, is governed specifically by the movement of electrons, so actually what we have modeled in this situation is equivalent to the same amount of negative charge flowing in exactly the opposite direction. Physicists had already defined electric current to be the flow of positive charge, and later found out that actually it's negatively charged electrons flowing in the exact opposite direction that generate current. Unfortunately, as a result, we're all stuck with the convention that current is the result of positive charge flowing. So we're going to stick with this model here, but you should keep in mind that electric current in metal occurs because of the flow of negative electrons in the opposite direction. Now then, we were wondering, how do we define current? Imagine we're watching a specific cross-sectional area in the wire. Over time, positive charge crosses this section, doesn't it? And the longer time we spend looking at it, the more charge crosses this section. So our formal definition for current is given by the following. Imagine we spend some time delta t looking at this cross-section. During that time delta t, we measure how much charge flows across the cross-section. Why don't we call that delta q? Then if we take delta q and divide it by delta t, this is the average current in the wire. That's it. That's our definition for current. It's the amount of charge that flows across this cross-section during some time interval, divided by that time interval. It kind of makes sense for a working definition, because you could imagine if all these charges were flowing at the same speed. As you wait a longer time interval, you have roughly the same proportional increase in the amount of charge that passes the cross-section. So the current stays roughly constant then, which we would hope. In order for the current to be higher, you need the charge to be moving faster, in which case more charge passes the cross-section over the same time interval. For the current to be lower, we need the charge to be moving slower, in which case less charge passes the cross-section over the same time interval. Now, for the calculus nerds, it'll be useful later to define this concept called the instantaneous current, or the current at a given instant in time. For that, we wait a tiny infinitesimally small amount of time dt, and measure how much charge dq passes the cross-section. Then dq divided by dt would give us the instantaneous current in the wire. This also leads us to the units for current. The unit for current is the ampere, defined such that 1 ampere is equal to 1 coulomb divided by 1 second. So we have all consistent units here. Now, going back to these animations here, what kinematic property is this reminding you of? We're changing something about the positive charges, or charge carriers, and that changes the electric current. It's the speed, or the velocity of the charges. When the charges have higher speed, the current is higher. When the charges have lower speed, the current is lower. Therefore, we expect the average speed of the charges in this direction to be somehow integrally related to the electric current. Let's figure out how. It's going to involve a bit of what seems kind of like magic, but we'll try and thoroughly piece it together. Let's start by introducing some time interval delta t and some cross-section A. So we measure how much charge is passing through this cross-section A over the time interval delta t. Okay, now that we're finished measuring, where does this crossing charge come from? If we make the simplifying assumption that the charges are moving at a constant speed, the charge that passes through this cross-section here can only come from one specific region, and that's this region right here. During our predetermined time interval, only charge within this region can end up passing the cross-section. Charge in any other region is either too delayed and never makes it to the cross-section during delta t, or the charge is already in front of the cross-section, in which case it will obviously never pass the cross-section again. It is precisely the charge in this region here, and this region only, that passes through the cross-section during our predetermined time interval. So now we're interested in how much charge exists within this specific region here. That information is going to help us figure out the current. The typical way we model charge flow is not really as one giant block of charge just moving through wire, but rather as individual charge carriers, maybe electrons or positive ions if we're talking about ion beams, but without getting overly technical, for the most part, current is carried by the same type of individual charge carriers in whatever material or substance we're looking at. In our simplified model, each of the charge carriers has the same charge Q, and why don't we say there are n of them within this region? Obviously we can see there are only 5 in this region, so n equals 5 here, but in reality n would be way larger, like think the density of electrons in a material larger. Then the total charge in this region, we can call it delta capital Q. It's just capital N times little q. It's just the total number of charge carriers times the amount of charge that each carrier has, whether the carrier is an electron or an ion or whatever. But if we keep going with this, we're going to end up in a bit of a rut. You see, n is going to change depending on how big our region is, so we need a measurement that's independent of the amount of charge in the region. For that, we can define lowercase n as the amount of charge carriers per unit volume. Then the total amount of charge carriers, capital N, is just the number of charge carriers per unit volume, lowercase n, times the volume itself, V. Because we have a cylindrical shape here, the volume of this region is just A times D, where D is the length of the region here. And it almost seems like we're going in the opposite direction, right? We started introducing more and more variables and we've gotten ourselves stuck with this complicated mess here. But here's where the magic comes in. Delta capital Q is the total amount of charge in the region, and we know that it's precisely the charge in this region, and that charge only, that passes through the cross-section during some time interval. Therefore, if we just divide both sides of the equation by delta t, the time interval, we end up with the current through the wire on the left-hand side. The current is just the amount of charge in that region, delta capital Q, divided by the time interval delta t, during which the charge passes through the cross-section. Now, what do we do with the right-hand side? I'd like to draw your attention to this expression right here, with d over delta t separated out. What is d over delta t? D is the length of the region, as we said before, but incredibly, d is also the distance that the entire region moves during the time interval. By construction, only this region moves through the cross-section during the time interval, so all of the charges move a distance of exactly this length d during the time interval. Then the average speed of the charges in this direction, v sub a for average, is just d over delta t. And this then is our final result. The average speed of the charge carriers in the direction of the current is defined by this equation here. Now, very often you'll see this equation written with v sub d instead, where v sub d indicates drift velocity. What does drift velocity mean? What do we mean by that? It exposes a flaw with our model. You see, in our model, we just have charge flowing perfectly smoothly in a single direction. But what about all the atoms and the impurities in the wire? Surely they get in the electron's way. Really, this is not how charge flows at all. Instead, v sub d characterizes an average drift velocity in the direction of the current. Before electric current exists, like when this metal wire is isolated and not connected to anything else, we might think of electrons as just having a propensity to move in random directions without any net current in any direction, or any net drift velocity either. But once we have electric current in the wire, like maybe we connect this wire across a battery, the battery has a potential difference between its terminals, which create an electric field in the wire. So now electrons begin to accelerate against the direction of the electric field, creating an overall average drift velocity of the electrons opposite the direction of the current. That's why we call it drift velocity. It's not the actual speed of the individual charge carriers, it's just the average drifting speed of them in the direction of the current, or in this case, because they're negative electrons against the direction of the current. So that's great. We now have a working model of electric current, or the flow of charge, but we're missing something. We know that the average drift velocity of the charge carriers themselves determines the electric current, but what determines the velocity itself? What controls the drift velocity of the charge carriers? An even better question, can we control the drift velocity of the charges? If we could control the drift velocity, that implies that we can control the current, which would have far-reaching consequences. We'll explore this question and answer it in the next video.